Hello. So this time we're going to the details about linear dependence and independence. And to that extent, consider the equation given by these vectors. What is this saying, right? Well, this says, or this indicates, and that we can express um, 1, 2, the vector, as a linear combination of the vectors 3, 4 and 5, 6. So, in a sense, we have that 1, 2 depends linearly uh, on these two vectors, right? Why? Because I can express this quantity vector, right, as this other two, right, showing that linear dependence, right? But now we have to think in a more abstract way. So, but not so high that it's impossible to relate it to the process, to the problem, to the current situation, right? So now suppose that we have three vectors. That I'm going to name as U, V, and W, right? We would say that the collection, with curly brackets just to indicate set notation, U, V, and W, is linearly dependent if there's an equation like the one that we have above. In other words, if one of the vectors is a linear combination of the others. This is, there are A and B such that we have U is equal to A V plus B W, of course A and B real numbers, right? Or you have V is equal to AU plus VW, or you have that W is equal to AU plus BV. But well, this is too many things to check, right? It's a lot of work. Can we write it in equivalent terms, right? Equivalently, you would have something along these lines. Negative 1 times U plus A V plus BW equal to the 0 vector, or you have AU plus negative 1 times V plus BW equal to the 0 vector, or you have AU plus BV plus negative 1 times W equal to the 0 vector. Well, that's still a lot of work. Right? However, we see that the only requirement is that not all the coefficients of u, v, and w are 0. Why is that? Well, say, for example, that you have something along these lines: du plus ev plus fw equal to the 0 vector, right? Where not all of d, e, and f are 0. You can say that e is different from 0, right? Then we can transform this equation that we have here into this. Into the following. Something that looks like this. Negative 1 over e, I would be able to make this division, right? And then multiply both sides of the equation, du plus ev plus fw equal to negative 1 over e times the 0 vector. Of course, you would distribute, and you will have negative d over e u negative v minus f over ew equal to the 0 vector, which you can now transform into v being equal to negative d over e times u plus negative f over e times w. Well, this would be your a and your b's, right, that you were looking for. Again, this can happen for either e, as we have done it, for d or for f, right? It doesn't matter for which one, as long as it happens for at least one of them, right? But this demonstrates, this particular case, this shows the linear, that v is a linear combination of the other two, right? In other words, the collection is dependent, of course, linearly, right? So, before we get into the actual definition, what would independence mean? Well, let's see. Right? Let's see. Well, in these terms, think about this. What is dependence? Well, dependence, would be the negative notion of independence, and similarly, the notion of independence would be the negative of dependence. So, let's put it in the following terms. What would happen? I will start like this. Dependent means there are D, E, F, not all of them 0, such that du plus ev plus fw is the 0 vector. So independence being the negation of dependence would be something like this. For each DEF, if DU plus EV plus FW is 0, then each of these ones are 0. But the 0, the number. So this motivates the following definition. Right? Just like this one. I would say a set of vectors like this: U1, U2, UK of Rn, meaning taking n entries, is linearly independent if, well, not if, but whenever we observed that A1 U1 plus A2 U2 plus blah 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 plus AK UK being the 0 vector, that indicates that each of A1, A2, and AK is 0. Boom. With this we finish. Right? We started from an example, right? That was the one that we had right here, right? This equation that motivated the notion of linear dependence. Also, we would say that this vector is in the span of these two. Then we expanded this notion to become a little bit more abstract. Then we indicated that dependence is a notion that only tells us whether we can write 0 as a certain linear combination, right, of the vectors involved. Linear independence being a negative notion, right, that would be just the negation of dependence, meaning that if you are able to express the 0 vector as a linear combination, right, just as we have here, that tells us that the only way in which we can do that is exactly when all the coefficients are 0. So, to summarize this and to put it in context, is the set given by 1, 2, 3, 4, 5, 6 linearly independent? Well, the answer is no. Of course not. We know, or we see, that we can write -1 times 1, 2 plus 2 times 3, 4 plus -1 times 5, 6 as the 0 vector. So it's not the only way to write the 0 vector as a linear combination of this when we have the coefficients being all of them 0. So while -1, 2, right? Well, next thing, how do we test for linear independence? Well, for that, subscribe and check my next video. Take care.